So today we're going to be looking at systems of forces part 2. We're going to be looking at pulleys. A pulley is where we have a wheel on which a rope or string or cable passes. And for the purpose of the mechanics in year 12, the two particles are going to either hang either side in a vertical way, or they're going to be going around the pulley and both going to be moving in a horizontal direction. It's not going to be any awkward angles. So let's have a look at drawing a diagram to represent the question, and then we'll look at what I mean by the question about tension in each part of the string in a minute. So particles P and Q of mass 2m and 3m are attached to ends of a light inextensible string, and that passes over a smooth fixed pulley. So I'm going to draw myself a pulley. It's smooth and fixed, which means there's no friction and it's not going to move. And the string is taut, so we have two masses hanging either side of this pulley. And we have one mass here, which is going to be of mass 2m, and another one of mass 3m. So you can see that we're going to have some forces here. We're going to have a weight here of 2mg and a weight here of 3mg. Now we're also going to have tension in the string. Now, this is where we talk about tension in the string being the same. So this tension here, I'm going to tell you that that tension and that tension are going to be exactly the same. And you should also we can also recognize that actually we'll also have tension equal and opposite in this direction that is going to be acting on the pulley itself. But because it's a smooth fixed pulley, we're generally not going to worry about that so much. But under what conditions is the tension on each part? So each part would be the left-hand side and the right-hand side. Under what conditions is it the same? Well, it's the same if it's a single piece of string and if it's a smooth pulley. So we have a single piece of string going over here, and the pulley is smooth. Therefore, the tension in that string is consistent and constant throughout that piece of string. If we have friction or multiple pieces of string, then the tensions would be different, and that's a really important key point. So how can we think about this? We can think about this in two sections, or we can spread this out into a single section, which makes things interesting. So let's think about splitting this up first, because I think that's the most logical way of thinking about it when you first start this kind of thing. So can we write down an equation of motion for P and for Q? So you can see that generally we expect this whole system to be traveling or accelerating, in this direction, because we have a greater force going over the pulley in that direction. So the acceleration should be in that direction. It might be initially moving in the opposite direction, but it does say in this case the system is released from rest, so it has an initial velocity of 0. The masses themselves don't give us any information about the initial velocity, it's just the acceleration. So if we think about the left of this, if we resolve our forces this way, the force is acting on the mass. We have T take away 2mg, and that equals our mass times by our acceleration. So our mass is 2m, and our acceleration in that direction is a. If we think about the right, then if we continue in that same direction, what we have is the string, the whole system bends around and then is heading downwards. So what we have in this direction is, if we follow the system as a whole, so what's up here comes down here. So really what we're doing is we're taking the system like that. Okay? So in the downward direction here, we have 3mg take away T equals mass times acceleration, so 3ma. Right? And those would be two equations of motion for P and Q. Now I've done it this way to make it easier when it comes to finding the acceleration of each mass. Because what I can do now is I can take equation 1 and equation 2 and add them together. And when I do that, I end up with, on the left-hand side, I get mg, because 3mg take away 2mg is just mg. And on the right-hand side, I end up with 5 MAs. And at that point, so this was equation 1 plus equation 2. Let's make sure I write that down. At that point, you can see that both sides of my equation have a constant factor of m, and g is 9.8. So 9.8 equals 5a. So I can then divide both sides by 5. So I get 1.96 for my acceleration of each mass. Now, the interesting thing about this is we don't necessarily have to always consider this to be two separate sides. Because if we think about the system as a whole, both objects are linked together by a taut string. So what we could do is we can imagine the system is one whole system, connected like this. And what we have is a force of 2mg in this direction. We have our tension here, we have our tension here, and we have the pulley in the middle, but the pulley isn't actually affected by anything, so I'm going to ignore that entirely. So all of the forces that affected the pulley, so this force and this force, I'm just ignoring them because they were only affecting the pulley itself. And then we have, in this direction, 3mg. So you can see what I've kind of done is I've stretched out this pulley system into a single line, and that helps me to be able to make this into one single system. You can see the total mass here is going to be 5m. And if I now resolve my forces in this direction, I have, one more thing. You can see I'm accelerating in this direction. So when I resolve my forces, 3mg take away 2mg is equal to my total mass, so 5m, times by my acceleration. So mg equals 5ma. You can see that the m cancels out, and we get to the place where we were before. We end up with our acceleration ends up being 1.96 meters per second squared, which is quite nice. But in order to find the tension in the string, we do need to consider one side only. So if I label that on my diagram, if I now go back to considering just the left-hand side, okay, then I have in this direction, because I'm continuing to take the direction of the acceleration as positive, then I have t take away 2mg equals, now my mass of the left-hand side is 2m, and my acceleration is 1.96, which we've just calculated. So I can end up with my tension equals 2 times 1.96. So 1.96, just get my calculator. We get 3.92. And then I've got to add my 2mg. So 2 times g is 19.6. So add 19.6 m. Okay. Right, so then find the force exerted on the pulley by the string. So this is where we have our tension on the pulley. So the total force exerted on the pulley, as you can see from the diagram, is going to be 2 lots of our tension. So this is going to end up being, because we have our tension here and we have our tension here, so it's going to end up being 2t. Let me just finish off that last question fully. So we had 3.92. This was 23.52 m. So 2t here is going to be 47.04 m. Okay, find the distance moved by q in the first 4 seconds, assuming that p does not reach the pulley. So if we assume that the particle, this was p and q, wasn't it? P and q. Assuming that p does not reach the pulley, what we have here is we have an acceleration, and we can now actually use Subat equations. So we don't need this at this point. We want to know how far it moves, the distance moved by q in the first 4 seconds. So if we think about our displacement, that's what we're trying to find out. Our initial velocity is 0 because we've been released from rest. We don't know what our final velocity is. We know our acceleration is 1.96 meters per second squared. And the time taken is 4 seconds. So assuming that it doesn't reach the pulley, find the distance traveled. So I'm going to call that x. So you can see that we should be using the Subat equation s equals ut plus half at squared. And because u is 0, we just have half at squared. So a half of 1.96 times 4 squared. So 4 squared is 16, half of 16 is 8, so it's 8 times 1.96. So we get 15.68 meters. I think that is every